Well, good morning, students. It's Thursday, March 19th, 2020. Day 4 of our strange new world. Trying to do video a little bit differently here today, but I think this format is going to work a little bit better for what I want to try to go over with you. Couple of just general comments along the way. I'm very concerned about are you able to access these videos, and of course if you're not able to access it, you're not hearing it, but you might be talking back and forth with some of your classmates, and if you know of their problems, please let me know. This is all brand new. A large part of my week has been trying to figure out, well, if this doesn't work, how do I do it again? If that doesn't work, how do I do it again? This student's having this problem, this student's having this problem. And that's one of the reasons why I've been a little bit slow on trying to get your stuff to you for daily lessons. I'll keep working at it. Be patient. The goal, remember, our goal is to try to learn some things. So, let's think back where we are. I want to revisit the idea of electron configuration, so we're going to try to get into some good, thorough practice on this today. So, we did electron configuration notation when you did the Electron Hotel. You just didn't know what it was at the time, okay? Remember when we booked people into Electron Hotel, if you had 10 people staying in the hotel, well, you put the first two in 1S, you had 1S2, and then you went to 2S, and you put 2 people in there, 2S2, then you went to 2P, and you could put 6 people in that one, 2P, 6, and you had 10 people in the hotel, 2, 2, and 6. Well, what that's all about, it's actually called electron configuration notation. And in electron configuration notation, you're basically kind of giving a map or a listing of where all the electrons are in an atom. And so it's going to tell us the energy levels, the main energy level. That's the numbers. So I have an example electron configuration written down here. 1s2, 2s2, 2p6, 3s2. The big numbers in front of the letters are representing energy levels. The first energy level, the second energy level, the third energy level, there, and over there. The sublevels are represented by those letters. S, P, D, F. Stupid people die first. So those 2 electrons are in the first energy level in an S sublevel. Those 2 electrons are in the second energy level in an S sublevel. Those 6 electrons are also in the second energy level, but they're in a P sublevel. And then we got the third energy level, S, P, eventually D, but there's a 4s that sneaks in there. The total number of electrons in the subshell are written as a superscript. A superscript is written a little bit above the line. That's like our exponents that we use in math. Those are superscripts. So 1s, superscript 2. 2 electrons in the 1s. So with that, how do we remember the order? And I want to remind you of a tool that we had. It's called the diagonal rule. So in the diagonal rule, if we start with 1s, and right below it we do 2s and a 2p. Below that we do a 3s, 3p, 3d. 4s, 4p, 4d, 4f. Remember, each level that we go down, each energy level has one more sublevel. After F, we would go G, H, I, alphabetical order. After the 4th energy level, we go to 5th, 6th, 7th, 8th. In theory, this gets infinitely big. In actual practice, the largest atom that we've ever had evidence for, and this was, through use of particle accelerators or atom smashers or whatever the terminology is, artificially produced on Earth, is element number 118. And it turns out you can put all of our atoms and their configurations within 7 energy levels and up to F sublevels. but please understand it does continue. Now when you have this written out, we start at the top and we do diagonal lines. So when you see this, after 4P would come 5S. Then we'd go back and start repeating. So if we follow the lines just in through order, 1S, 2S, go to the next line, 2P, 3S. 3P, oh, there's that 4S that's sneaking in there between the P and the D on the third energy level. 3P, 4S, 3D. And so you have this written out. This is a tool, again, it's a diagonal rule. You are welcome to use that on all your work. You're welcome to use this. Now, that said, this is the only thing that you're supposed to have written down here. I do expect you to try to remember how many electrons can go in these. Now, there's a pattern. When we talk about orbitals, when we went through our quantum numbers, we talked about orbitals within the sublevels. The S sublevel only had one orbital. The P sublevel had 3 orbitals. The D sublevel had 5. The F sublevel had 7. There's a pattern, 1, 3, 5, 7. So we can guess that the G sublevel would have 9 orbitals. Now let me tell you that every orbital can contain up to 2 electrons. Well then, if there's one orbital here, that can contain 2 electrons. 3 orbitals here can contain 6 electrons. 5 orbitals can contain 10 electrons. 7 orbitals can contain 14 electrons. 2, 6, 10, 14. If we went to the next one, it would have 18 electrons. So we got to remember that part. You may have the diagonal rule written down. You've got the half sheets already. Keep them handy. Keep them with you when you're working. Okay? So let's write out an electron configuration. So I'm going to pick an element. I'm going to go with bromine. Bromine is number 35. Okay? And so we should remember that that means it's got 35 protons and it's got 35 electrons. And we'd have to have information to figure out the number of neutrons. If we look at the periodic table and see that bromine is about 80, that would suggest it has 45 neutrons. Bromine is one of those weird ones. There's actually a bromine 79 and a bromine 81 in about a 50-50 mix. So the average ends up being 80, even though there's no bromine 80. Not important for us right now. What I want to know is the 35 electrons. So follow along with the diagonal rule, but everybody should be up to date by now that the first electrons go into the 1s. How many electrons can go into 1s? 2 electrons can go in there. There's 1 orbital, 2 electrons. Now that's full. So we go to the next one, 2s. 1 orbital, it can hold 2 electrons. Follow your arrows. After 2s, it's going to come 2p. The p subshell has 3 orbitals, so we can hold 6 electrons. Now I want to kind of keep track. So far I've used 10 electrons out of 35. 25 to go. After 2p is going to come 3s, 1 orbital, 2 electrons. After 3s comes 3p, 3 orbitals, 6 electrons. Here's where we got to be careful. It's not 3D. The next lowest energy orbital is in the 4s. 1 orbital, 2 electrons. If you count, 2 plus 2 is 4, plus 6 is 10, 12, 18, 20. I've used 20 electrons. I got 15 to go. So after 4s, we start the next line on our diagonal rule. We're going to have 3d. Now the d subshell has 5 orbitals. That's 10 electrons. I could put all 10 in here, and suddenly I went from 20 to 30 electrons. I only have 5 more. After 3d comes 4p. The p subshell has room, well, it has 3 orbitals, so it has room for 6 electrons, but there's only 5 left, so it's not full. The only subshell that you're going to write out that's not going to be full should be the last one. We're going to find out a little bit later that there's a couple of exceptions to that. But in general, the only subshell that's not going to be full is the last one. Okay? Think about it. Orbitals can either be empty, they can be full if they have 2 electrons in them, or they can be partially filled with 1 electron. They can only hold up to 2, so partially filled is 1 electron. So these orbitals are all full. Right there, the p subshell has 3 orbitals. And if we look at those orbitals, what we often do is we draw lines to represent the orbitals. There's my 3 orbitals. This altogether is in the 4p subshell. And then we look at our electrons. There's 5 electrons in there. And so they have to have opposite spin if you remember our quantum numbers. We represent the spin of electron with an arrow. And an up arrow is going to be a positive spin, and a down arrow is going to be a negative spin. So 5 electrons go 1, 2, 3. You put 1 in each. And then you come back and you start doubling up. 4, 5. So this is another notation that shows a little bit more information. Electron configuration is what we had right here. This is using a little bit of what's called orbital notation. In orbital notation, usually we use it for just looking at a specific subshell. We could write out orbital notation for everything here, but orbital notation breaks down each of the orbitals and shows how the electrons are arranged. Positive spin, negative spin. If we look at this, we can see that within the subshell, we've got 2 orbitals that are full, and then we have 1 partially filled. That's going to be really important for when we talk about chemical bonding. Hopefully this shows up okay. If you look on the bottom of my screen here, what I did is I very carefully wrote out an electron configuration for a lot of electrons. I went all the way up to 8s2. That's bigger than any real atoms that we know of on Earth. And I have to be careful with this. I have to get it 100% correct because I'm going to use that to help me with exercises. You're going to have an assignment today where you're going to do multiple exercises. If you have one accurate configuration written out, it'll be very helpful. If you make a mistake in it, you're making mistakes on everything you do. So this part has to be right. Here again, I'm doing the same thing. I wrote out an electron configuration for 120 electrons. So when you write yours out, you could pause on this for just a little bit and you could look through and try to see, did you match? Now you see these red numbers I wrote in? That's not actually part of the configuration, but that's me just doing a little counting and say, all right, at this point I'm up to 10. At this point I'm up to 20, 30, 38, 48, and just trying to keep track that I'm up to right here 120 electrons. And that's useful actually to write in a few of those numbers too when you're giving yourself a tool to use. Skip over a couple of these pages. All right. You read about in your assignment in the book 3 principles about quantum numbers and electron configurations. And I do want you to know the names of these principles and be able to give a statement of them. So the Aufbau principle. Aufbau comes from German, and it literally means to build up. Okay? Aufbau means to build. So this, when you use your diagonal rule to fill electrons into an electron configuration, and you're going from the 1s to the 2s to the 3s, the reason you're doing that is because that's the orbital of increasing energy for our subshells and our energy levels. And so really when you use that, you're filling the atom from the lowest energy first and you're filling it up. You're using the Aufbau principle. So the diagonal rule could also be called the Aufbau principle, the Aufbau rule. What it says is that you always fill electrons into the lowest energy orbital that has room for them. So if there's room in the 1s, you're putting electrons there before you fill it anywhere else. Our second rule is called Hund's rule. Again, a good German name. Poor guy. Hund is actually the word for dog in German, so this is dog's rule. If you have orbitals of equal energy, you have to fill one electron into each orbital before doubling any up. When I was showing you that orbital notation just a little bit ago, we had 5 electrons in that p subshell. And the p subshell, I said, has 3 orbitals, so I drew out 3 lines for my orbitals, and I put an electron there, and I didn't put the next electron right next to it. If you have orbitals of equal energy, you put 1 electron into each. So my second electron goes there, my third electron goes there. Now they each have 1. I can start doubling up. Excuse me. I'm coughing a little bit, sniffling a little bit. I have seasonal allergies, so don't worry. There's my 5 electrons split up. 2 of the orbitals are filled, 1 orbital is not filled. Spoiler alert, that guy's going to want to fill that up. When we get to chemical bonding, that is important. Our third of our rules or principles is the Pauli exclusion principle. And it says no 2 electrons in the same atom can have the same set of 4 quantum numbers. Okay? To be exclusive, if I say you have exclusive access to something, it means it's one of a kind. You are the only one. That's what exclusive access really means. So we're saying that every electron has its own exclusive set of numbers. Now, I could have 2 electrons that are in the same energy level, they're in the same sublevel, they're in the same orbital, but then they have to have opposite spin. Okay? I'm going to just insert a page here. Let's get a reminder about our quantum numbers. So we had the principal quantum number, and the principal quantum number has the value n, or the symbol n. It's basically about distance from the nucleus, and in our electron hotel, it was represented by the floor. What floor were you on? We have the orbital quantum number. Its symbol is L. It's telling us about the shape of the subshells, or the orbitals within the subshells. And from our electron hotel, it would correspond to the room on the floor. And then we have the magnetic quantum number. Its symbol is M. It's telling us about the orientation of the orbital. So, if you remember my balloon models, we say that a p subshell has 3 p orbitals. Each of the orbitals represents, this top lobe and this bottom lobe would be an orbital. It's that dumbbell-shaped orbital. And this lobe and this lobe represents an orbital. And the one in front and the one in back represents an orbital. So, together, when these things come together in the subshell, they're trying not to overlap with each other, and so they are oriented in 3 different directions. So, the magnetic quantum number is saying, is it this orbital oriented this way, or is it the orbital that's oriented this way, or is it the orbital oriented this way? I'm just going to add in here orientation of orbital. In our analogy with the electron hotel, this would have been the table. And then finally we get the spin quantum number. And a spin quantum number is given S. And this is the orientation. So again, a little bit confusing. But this is talking about the orientation of the electron within. So the electron has a spin. It's either got a positive spin or a negative spin. It's either got a clockwise spin or a counterclockwise spin. This is representing the person sitting at the table in our electron hotel. These are going to be positive whole numbers. These are going to be numbers ranging from 0 up to n minus 1. These are going to be from negative L to positive L. These are going to be positive 1/2 or negative 1/2. You have notes from last week on this. This is just supposed to be a little bit of a review. I hope you go back and look at that. All right, so we're going to work through a couple of example problems yet, and then I'm hoping that you have the skills that you can practice. So here's our question. We're going to find a set of quantum numbers that describe the last electron in chlorine. So I went ahead and I've written out a very long electron configuration. This goes up to 112 electrons. So I not only did the configuration, but I put in some reference numbers so I know how many electrons are. That's going to help me answer this quickly, because what I'm going to do is I'm going to look at chlorine. I look at a periodic table and I see chlorine is number 17. So that means 17 protons, 17 electrons. We're talking about electrons here. So 17 electrons. Now, I can look up here and say 18 electrons would be everything up to this. We'd have 1s2, 2s2, 2p6, 3s2, 3p6 takes us to 18. So 17 is one less. So 17 electrons would have everything up to 3p5. Okay, I can figure it out. So I could write that all out if I want, but that's not the purpose of the question. The purpose of this question is not to write an electron configuration. It's trying to figure out the quantum numbers for the last electron. So I want to know the 17th electron. 17th electron in chlorine, and this tells me where that 17th electron went, because that number right there tells us the first quantum number. That's the energy level. So the energy level is the first quantum number. My first quantum number is 3. Okay? That letter right there tells me the second quantum number, because if you remember, stupid people die first. S had a value of 0, P had a value of 1. D is 2, F is 3. Stupid people die first. P is a value of 1. My second quantum number is a 1. Okay, now how do I find my third quantum number? This is where we want to break out the orbital notation. We want to say, in a p subshell, there's 3 orbitals. So I'm going to draw 3 blanks. Please take the time, use paper. Paper's cheap. If you run out of paper, contact me, I'll get you some. I'm going to draw out 3 blanks to help me see this, to help me visualize those 3 orbitals. And what I know for my third quantum number is the possible values for that quantum number range from the negative of this up to the positive. So if this is a 1, I'm going to start here at negative 1, and then here's a 0, and here's a positive 1. Those are my 3 possible values for the third quantum number in this case. Now, there's 5 electrons in here. I'm going to use Hund's rule to distribute those electrons. 1, 2, 3, there's 1 in each. Go back and double up, 4, 5. Where did my 5th electron, the last electron, ended up? It ended up right there in the 0. Now, that electron, this one right here, was the second electron in that orbital. The second electron in that orbital gets a value of negative 1/2. Now, do all of these electrons have different quantum numbers, like the Pauli exclusion principle says? all of these 5 electrons are in the third energy level into p sublevel. But you see they're distributed between 3 different orbitals and 2 different spins. So this electron would have been a -1 plus 1/2. This electron would have been a -1 minus 1/2. This electron is a 0 plus 1/2. This electron, the one that we were looking for, was a 0 minus 1/2. This electron is a +1 plus 1/2. The question says find the set of quantum numbers. Here is our set of 4 quantum numbers that describe the 17th electron. Now, not only in chlorine, but if you wanted to talk about the 17th electron in any atom, there you go. Oh, let's do one a little more interesting. There's boron. All right, let's try uranium. So, find the set of quantum numbers that describe the last electron in uranium. I'm going to look at my periodic table. I see uranium is number 92. So I got to go out here. I got to find 92. 7s2 has 88. So I need 4 more. So my next subshell is 5f. And if I need 4 more than the 88, I must have 5f4. That's my best guess. So I know I'm going to have everything up to 5f4. Now what? Well, my first quantum number is told right there. It's a 5. My second quantum number is represented by that letter. Stupid people die first. Second quantum number is a 3. Okay. Now I'm going to break out the orbital notation. If that's a 3, I'm going to range from -3, -2, -1, 0, 1, 2, 3. The F subshell has 7 orbitals. There are 4 electrons distributed in those orbitals. Hund's rule says put 1 in each before you double up.